Hey everyone, I'm Nick, and this is Bits of Architecture. So in this episode of the series, we're going to be talking about the multi-core era in computer architecture. So in the previous video, we talked about things like the power wall and the end of Dennard scaling. Now, one of our key takeaways from that video was that we can no longer scale frequency in the same way that we had in previous decades. Now, a good follow-up question to this is, of course, now what? So what do we do now that we can't scale frequency in this same way? Right? Does this mean the end of our performance improvements? Well, the fact is that frequency did drive a lot of our single-threaded performance. So if we were able to double the frequency of our processor, basically all of our applications would see a 2x performance improvement. Now, despite the fact that we can no longer scale frequency in this way, we are still getting more transistors, albeit a lot more slowly now. So we are improving from, say, 14 nanometer processes down to 10, down to 7, down to 5, and even down to 3. So we still have a lot more transistors to work with that we can use to improve the performance of our processors. But how exactly do we allocate this silicon? So one train of thought, right, we could say allocate it towards to make a very large unicore processor. So basically our entire chip is a single core. So we could allocate these extra transistors towards our branch predictors, towards our reorder buffers, and towards our, say, vector hardware. So either wider vector instructions or just more, vector units in general. So the problem with this is that there's diminishing returns on each of these things. So if there's diminishing returns we get from improving our branch predictors, there's only so much instruction level parallelism to exploit with making wider and wider reorder buffers. And the fact is we don't actually see any performance improvement from our wider or more vector units if our actual programs can't make use of them. So while it might seem nice that we have, say, AVX 512 instructions today, we have to have a program that can actually use those AVX 512 instructions, right? And has that kind of parallelism to exploit in the first place. Otherwise, that silicon kind of just goes to waste. Now, another thing that we can do is instead of making these larger, single beefy core processors, is we can allocate the silicon to having greater than one core. So maybe smaller, less powerful cores, but more of them. And this is really what happened in that kind of 2004 to 2006 timeframe. We went from the single core era into the multi-core era, where we started building chips with greater than one core. So why exactly did this work, right? Why do we have basically exclusively multi-core processors today? Well, multi-core is all about exploiting parallelism. So the fact is that we often want to run many programs at once, so we can run these programs independently on our different cores. And the fact is that many of our programs even have independent sections, right? So while one core is, say, working on part A of a program, another core can be working on part B of a program, right? And many programs have these characteristics. So multi-core or multiple cores allow us to exploit these things. Now, everything isn't, say, sunshine and daisies, right? Multi-core can actually be quite difficult. So fundamentally, parallel programming is performance programming. And when we're programming for multi-core processors, this can become incredibly difficult, right? So parallel programming breaks our layers of abstraction, right? So programmers suddenly need to know about the underlying hardware, right? So instead of just writing, say, their high-level application saying what they want to do, now they're thinking about partitioning their work across different threads so that it can be parallelized, right? And this can be quite tricky. It can be tricky for a few different reasons. So number one, it can be pretty tricky to get something that's functionally correct, right? So making sure that you're using things like synchronization primitives in the right way, and making sure that you don't have, say, two threads that are writing to the same location at the same time, or making sure that you're serializing access to a piece of memory. All of these things can be quite difficult to do, especially for complex applications. Now, apart from just your program being functionally correct, it can be difficult to actually get the performance for complex applications. So it can be very easy to write a multi-threaded application that's slower than its single-threaded counterpart. And we also introduce new problems that we have to think about. So things like coherence, right? We have to make sure that we have coherent caches within the different cores of our processor. Now, clearly we're in the multi-core era. All of our CPUs that we use kind of commercially in desktops and laptops are these multi-core chips. But does this mean that kind of multi-core will live on forever and that there's no problems with it, even though it is a bit more difficult to program for? Well, there's some very interesting work that came out, say, back in 2011 related to multi-core scaling. And it was this paper called Dark Silicon and the End of Multi-Core Scaling. And this was, I believe, at ISCA in 2011, ISCA being a major computer architecture research conference. So the main idea behind this paper was that, transistors keep getting smaller, at least for now. And with all these extra transistors, we keep making more and more cores. But we still have to think about the fact that Dennard scaling is over. So we're having more and more transistors in the same kind of area. But we have this problem related to power, right? And the heat dissipation that we have from our processors. And the fact that, we've reached kind of the end of Dennard scaling and there was this breakdown of these scaling laws, right? We have all these extra transistors, but we can't actually turn them all on at once, which leads to this thing called dark silicon, which basically means that you can't actually power up your entire processor at once. Some of your processor has to be basically left off, right? And that's what's known as dark silicon. And that's because of these thermal design power constraints that we have. So it's a very interesting thing to think about, and I would encourage you to, say, read this paper. It's quite an interesting overview of the problem. But that's going to go ahead and do it for this episode of the series. As always, I'm Nick, and I hope you have a nice day.